Okay, guys. So last time we saw Article 2.5 and Article 2.5 that was based on the additive rules, in which we saw the additive of the events A union B equal to probability of A plus probability of B minus A intersection B. If A and B are mutually exclusive events, in that case, probability of A union B is equal to probability of A plus probability of B. And then after, we can extend the same idea for n number of sets or n number of events in the sample space. And then after, we saw the complement of an event, that probability of A plus probability of A complement, that is always equal to 1. And then after, we went over a few of the examples from the exercise. And today we are going to start the new article, that is the conditional probability. This conditional probability, article 2.6, that is the base for the next article, that is the Bayes theorem. So let's go for this one. Let me start let me show you my book. So let me first find the book. Where is my book? Just give me a minute and let me try to figure it out, the book. Okay, that is here. So conditional probability, that means the probability of an event B. We are looking for the probability of an event B with the condition that event A has already occurred. Whenever whenever we are looking for the probability of an event, when one event is already occurred, with that condition, that's why it is called the conditional probability. Again, we are going to see the conditional probability in two cases, that whenever you have the mutually exclusive events and you have the means dependent and independent events. So you can see over here the probability of an event B occurring when it is known that some event A has already occurred, and that probability, that is called the conditional probability, and that is given by probability of B given A. This one is read as probability of B given A. That means the probability that B occurs given that A occurs, or A has already occurred. And that is read as I told you, probability of B given A. I would like to give you a very nice example over here. The example is given in terms of lines. And then after, I will try to explain to you what it actually means. So it says that, okay, it says that consider the event B of getting a perfect square when die is tossed. Now, when you toss a die, that means we have 6 outputs. That is either 1 or 2 or 3 or 4 or 5 or 6, because there are 6 numbers, 1, 2, 3, 4, 5, 6 numbers on a die. So if you roll a die, if you toss a die, at that time you have sample space 1, 2, 3, 4, 5, 6. And it says that my event B, that is occurring as a perfect square when a die is tossed. Perfect square, that means if I take, suppose S is my sample space, if I take 1 square, so 1 square is 1. Then 2 square is 4. 4 is over here. So I can write my set B equal to 1 and 4. But if I take 3 square is 9, which is not the part of the set. 4 square is 16, 5 square 25, 6 square 36. These are not the part of this sample space. So that means I'm going to take just 1 square is 1 and 2 square, that is equal to 4. So 1 and 4, these are the only 2 outputs. Right? So my event B, I would say that is equal to 1 and 4. Now, again, there is the same condition which I gave you last time. Last time I mean to say that when I was doing article 2.5, at that time we went over one of the examples, and that example was something like this. Let me just give you that one. That is not article 2.5, but article 2.4, I think so. A die is loaded in such a way that an even number is twice as likely to occur as an odd number. Twice as likely to occur as an odd number. That means here my sample space, you can see here my cursor, look at the cursor, when 1 is an odd number. That means how many 1 is an odd number, so it is 1. But 2 is an even number. That means it is twice as likely to occur. Whenever it is even number, it is twice as likely to occur as an odd number. So here it is 2, because 2 is an even number. 3 is an odd number, so 1. 4 is an even number, so again 2. 5 is an odd number, so again 1. 6 is an even number, so again 2. So if you add up all these things, 1 plus 2, 3 plus 1, 5, 3 plus 1, 4 plus 2, 6 plus 1, 7 plus 2, 9. That means total numbers are 9. That means the probability of getting 1 is 1 by 9. Probability of getting 2 is an even number, so it is 2 by 9. Probability of getting 3 is nothing but 3 is an odd number, so again it is 1 by 9. Probability of 4 is an even number, so it is 2 by 9. 5 is an odd. Probability of 5, that is again 1 by 9 because odd number. 6 is an even number. Probability of 6 is 2 by 9. So like this. Now, so that means my probability of getting, so what is the probability of B? B is 1 and 4. So probability of 1 is nothing but 1 by 9, and probability of 4, that is even number, so that is 2 by 9. 1 by 9 plus 2 by 9, that is 3 by 9. 3 by 9 is 1 by 3. That's what is it is written over here. The probability of B, look at my cursor, the probability of B occurring is 1/3. Actually, it is 3 by 9, so 1/3. Right? Then after we are given one set A, we are dealing with suppose that there is it is known that the toss of die is resulted in a number greater than 3. So I have one event in which all the numbers greater than 3. Greater than 3 means 3 is not inclusive. Means we have 4, 5, and 6. So these 3 numbers are there. So my event A, that is equal to 4, 5, and 6. So please try to understand this thing. It says that S is equal to 1, 2, 3, 4, 5, 6 with the probabilities 1 by 9, 2 by 9 assigned respectively as even and odd numbers, as I explained to you. Probability of B is 1/3. Also I explained to you. Again, I'm going to write all these things on a whiteboard, so just wait. Now suppose that it is known that the toss of a die resulted in the number greater than 3. Greater than 3, that means 4, 5, and 6. So my A is equal to 4, 5, and 6. Again, 4 is an even number, probability is 2 by 9. 5 is an odd number, 1 by 9. 6 is an even number, again 2 by 9. So 2 plus 1 plus 2, that is equal to 2 plus 1, 3 plus 2. So that is equal to 5. So it is 5 by 9. So probability of B, that is equal to 5 by 9, which is a subset of S, of course. And to find the probability of B, given A, when A has already occurred, that is given in this way, probability of B given A, that is equal to, don't read this part, just jump over here. Try to look at my cursor, just jump over here from here to here. So probability of B given A, that is equal to probability of A intersection B divided by probability of A. Probability of A intersection B, what is the common probability? The common number, B is nothing but 1 and 4. A is nothing but 4, 5, 6. The common number is just 4. So A intersection B is 4. 4 is an even number. Even number means probability is 2 by 9. So A intersection B probability is 2 by 9. Now come back to left side, 2 by 9. Same way probability of A. A, how many numbers are there? 1, 2, and 3. 4 is an even number, 2 by 9. 5 is an odd number, 1 by 9. 6 is an even number, 2 by 9. So 2 plus 1, 3 plus 2, 5. So it is 5 by 9. That's why the 5 by 9 is written over here. So if you cancel this 9 and 9, that means you're going to get 2 by 5. So probability of B given A, that means probability of getting the square of the numbers from the die, that is given that all the numbers are strictly greater than 3. Given that all the numbers are strictly greater than 3, that is 2 by 5. Means probability of 4, because in the A intersection B is just 4. So probability of B given A, that is 2 by 5. So that's how we can find the probability. Now, you know the complete example. I'm going to explain all these things in terms of the mathematical language on the whiteboard. So just let me stop sharing this book and let me go for my whiteboard. So look at over here, the whole example. Now you know these things, so I can write this one very quickly. So B given probability of B given A, that means equal to B given A, that means equal to probability of event B, that is probability of an event B given that A has already occurred. That is the meaning. Now we are looking for roll or toss a die, roll a die, and you're going to get 1, 2, 3, 4, 5, and 6. Condition is even number is twice as likely to occur as an odd number. Even number is twice as likely to occur as an odd number, as likely to occur. That means that probability of 1 that is equal to 1 is an odd number. So this is the odd number. So it is, here it is 1, 2, even numbers, so probability is 2, 3, odd number 1, 4, even number 2, 5, odd number 1, 6, even number 2. 2 plus 1 plus 2 plus 1 plus 2 plus 1, that is equal to 9. So total is 9. That means probability of 1, because 1 is an odd number, 1 is an odd number, that means it is 1 over 9. Same way, probability of 2 is an even number, so naturally that is equal to 2 over 9. Probability of 3, that is equal to again 1 over 9 because odd number. Probability of 4, that is 4 is an even number, so again it is 2 over 9. Probability of 5, that is equal to again 1 over 9 because odd number. Probability of 6, even number, 6 is an even number, so again it is 2 over 9. So just keeping this thing in mind, I'm going to write my another event, B given A. So B is the event, let me first write the B. B is the event, or B is the event of getting perfect square when a die is tossed. Perfect square, getting perfect square when a die is tossed. And A is the event. So getting perfect square when die is tossed, that means, as I told you, this is 1 and 4, because 1 square is 1 and 2 square is 4. Otherwise, all the numbers, they are outside the sample space, so they are not allowed. So 1 and 4. A is the event. What is my A? A is the event, number strictly greater than 3. Number strictly greater than 3. That means it is 4, 5, and 6. Again, 4 is an even number. This is an odd number. This is an even number, right? So probability of 4, you know this thing that is 2 by 9, 5 is 1 by 9, 6 is 2 by 9. 6 is 2 by 9. So here it is, probability of 4 is 2 by 9 plus 1 by 9 plus 2 by 9, and that is equal to 5 over 9. So probability of A, I would say, probability of A, that is equal to this one, 5 over 9. So I found, and here probability of B is nothing but probability of B, that is equal to 1 is an odd number. So it is 1 by 9, and 4 is an even number. So 2 by 9, that is equal to 1 is 3 by 9. So that is equal to 1/3. So probability of B is 1, probability of A is 5 over 9. A is 5 over 9. We are looking for the probability of B given A. Probability of B given A, that is equal to probability of B intersection A divided by probability of A. B intersection A, that means you can write A intersection B. So what is A intersection B now? Set A is this one, B is this one. So A intersection B is simply one element, 4. 4 is an even number. 4 is an even number, that means probability of A intersection B, that is equal to 2 over 9. That is equal to 2 over 9. So A intersection B, or you can say B intersection A. So both are same. So this is 2 over 9. Probability of A, already I figured it out, that is equal to 5 over 9. So that is equal to 2 by 5. So this is the probability of getting perfect square when a die is tossed, given that your number must be greater than 3, 4, 5, and 6. So that's what we mean by this one. So, and this is the example given to you. This is just the illustrative example, you can say, but this example gives information. So let me just save this page, and then after I can clear this screen, and again, let's go back to our book. So let me save in the folder, okay, and save it. And let me clear all the drawings. Okay. And let's again go back to the book. So that's what is mentioned over here in all these lines. But now I hope you guys will be probably able to understand this concept. And this is the definition 2.10 you can see over here. Probability of B given A, that is equal to A intersection B and probability of B. At the same time, I just would like to explain to you that probability of A intersection B can also be written as probability of B given A times probability of A. If you multiply throughout by probability of A, this will go over here. That is called the intersection rule. Probability of A intersection B is probability of B given A, conditional probability for the intersection of two events. Conditional probability for the intersection of two events. You can say like this. Okay. Now, another example is over here. Look at here, guys. The example is, suppose that our sample space S is a population of adults in a small town who have completed the requirements for the college degree. And we shall categorize them according to their employment status. That means male and female are there. How many males are there in the town? 500. How many female are there? 400 female. Out of these 500 males, 460 they are employed and 40 are unemployed. Female 140 are employed and 260 are unemployed. So total number of male and female in the town, they are 600. As total number of employed people in the town, they are 600. Total of unemployed in the town, they are 300. So 6 plus 3, that is equal to 900. So this side, look at my cursor, this side and this side numbers must be matching over here. Number must be matching over here. Now, the question is, suppose M stands, this capital M stands for a man, male is chosen, you can say, or a man is chosen. And E capital E stands for that chosen man is an employed. Chosen man, or the one who's chosen is employed. Right? And we are looking for the event that a man is chosen given that he is an employee. He is employed. Man is chosen given that he is employed. So probability of M intersection E is equal to, use this definition, look at the cursor, definition 2.10, probability of A intersection B, I would say B intersection A divided by probability of A. So probability of M intersection E. M intersection E means male and employee. Male and employee means 460 out of 900. So I would say 460 out of 900. 460 divided by 900. That is probability of M intersection E. M intersection E, that is equal to 460 divided by 900. Same way, denominator is probability of M given E, probability of M intersection E divided by probability of E. Probability of E, employed person, how many employed are there? Including male and female, 600 out of 900. So 600 divided by 900. That means you are getting probability of M given E, that is equal to 460 divided by 600, 23 divided by 30. That is the probability. Exactly same thing is mentioned over here, whatever I explained to you, that number of E intersection M and blah, blah, blah. You know this thing. Probability of E is nothing but means employed is 600 divided by 900. That's what mentioned here. E intersection M means employed and male. That means 460 out of 900. So 460 out of 900. So that is this one. So if you use this definition 2.10 mentioned over here, definition 2.10, if you plug the value, probability of M given E is M intersection E divided by probability of E. You have probability of M intersection E, you have probability of E, plug these values over here, and finally you are getting 23 divided by 30. So either you can go for this one, just the tabulated form, or you can use definition 2.10, and you are getting the same answer, 23 divided by 10. I can just twist the example slightly, that suppose I am looking for the probability of female, those who are employed. So instead of man, now female, I would like to denote capital F for a female is chosen. Female is chosen. The female is chosen, right? How many probability of female? How many female are there? So probability of female, I can write like this, given that she is an employed. So it is probability of F given E. Probability of F given is by definition 2.10, F intersection E. E employed M female 140 divided by 900. So F intersection E, that is F intersection E is 140 divided by 900. And probability of E remains the same because we are looking for employed, that is 600 divided by 900. So your answer will be 140 divided by 600. 140 divided by 600. That is the answer for the probability of, conditional probability of female. If female is chosen, given that that female is employed. So you can write that number. Same way, suppose I said M and which is unemployed. So I can say M given that E unemployed means I would say E dash, right? E dash or something like that. Same way you can find probability of female who is unemployed, given that she is unemployed, that probability. So same thing, once you have a tabular form, you can come to know lots of information based on this tabular form. So that's what we mean by the conditional probability. I just would like to go over one more example. That's very nice practical example. It says that the probability of a regular scheduled flight departs on time. See, departure, that means I would like to write capital D for the departs or departure, and probability of D, that is 0.83. Same way the arrival time of the flight arrivals or flight arrives, because capital A stands for the arrival, and that is 0.82. And the probability that flight departs and arrives on time, departs on time, and that's why, or arrives on time. So D intersection A, that is equal to 0.78. Find the probability that a plane arrives on time, given that it departs on time, and depart on time, given that it arrives on time. So we are asked to find two types of probability over here. Just look at over here what is given to us, and I will let you know this thing. So first of all, look at these two questions too, because I'm going to switch over to the whiteboard. So the two questions are there. Arrives on time, that means A, probability of A, given that it was departed on time. So probability of A given D. Okay, B part, departed on time, probability of departed means capital D, departed on time, given that A was arrived on time. So given that A. So these two probability, please make sure that A given D and D given A both are different events, and that's why answers are different. Please, it will not be the same answer. So please keep in mind this thing. Let me again stop sharing this thing and let me go back to my whiteboard. So my whiteboard here is, first of all, let me write it down. Example number 2.34. So it is 2.34. It says that probability of, let me write down this number. So probability of the flight departs, that is equal to 0.83. Probability of flight arrives, that is equal to 0.82. Probability of flight departs and arrives on time, departs and means intersection, arrives on time, that is equal to 0.78. And now we are going to answer two questions. The first question, arrives on time, given that it is departed on time. Arrives on time means A, given that it was departed on time. So D, and we are looking for this probability. By rule number, or I would say theorem number 2.10, we can say that probability of A intersection D divided by probability of D. Now probability of A intersection D, that is given to you, D intersection A and A intersection D, they are same. So 0.78 divided by probability of D, that is 0.82. Whatever the number you're going to get, that is the number when flight arrives on time. Probability of flight arrives on time when it was departed on time. B part is departed on time given that it has arrived on time. Departed on time given that it has arrived on time. So that is the meaning. When the flight is arrived on time, so it is departed on time. So that is equal to probability of D intersection A divided by probability of A. Again by theorem number 2.10. Theorem 2.10. If you apply this one, A intersection B 78 and probability of A that is equal to 0.82, you can, my bad, D was 83. So here it has to be 83, sorry, my bad. And here it is 82. So whatever the number you are getting, that is the answer. So this way, please make sure that both these answers, they are different. They are different. These two answers are different because they are two different events. Two different events. Okay, now I would just like to switch this example, something like this. Suppose somebody asked me, let me consider this thing, that I would like to find the probability of the flight arrives on time, given that it was not departed on time. So flight arrives on time, given that it was not departed on time. It happens very, very rarely. Otherwise, if you have a long distance flight from one country to another country, from here to United Kingdom, US to United Kingdom, US to India, at that time, suppose your flight is half an hour late because it did not departed on time. It was half an hour late over here, right? That means that, but even though it arrives over there, probably in London or Mumbai in time, so that because it's a long distance, sometimes flight covers the time by increasing the speed, but that happens very rarely. So that is given something like this, that probability of A intersection D complement divided by probability of D complement. Probability of D complement. Now guys, it is really very interesting. A intersection D complement, in your book, the answer directly is given, but that is without any understanding. So please make sure what does it actually mean. So that's what I would like to explain to you. When flight, because this is a kind of complementary event. So flight arrives on time, given that it was not departed on time, right? So that is by rule number or theorem number 2.10, we have this definition. But it is hard to understand. Well, how can I write this number? Because it's not given to us. We are given just these options. So I would like to go for the Venn diagram. Try to look at over here, guys, and I would like to write it down, my numerator in a simplest form. This is suppose my event A. This is suppose my event D, and I am looking for A intersection D. Now, what will happen that suppose I go for A, event A. Event A is this one. This is my event A. D complement means this one. These, everything outside D complement means this one, this. Not even this one, outside. D complement. So you can see over here, what is my common factor? This is my common portion. Here. This one, and this one. This is my common portion. How can I write my common portion? That's means by A intersection D complement. Do you think that this A intersection D complement means I can write that probability of A minus, because probability of A is whole part, and I want to exclude this one. I want to remove this part. So probability of A intersection D. Shall I write like this? A intersection D complement can be written in the form of probability of A minus probability of A intersection D. I can remove this part, and probability of D complement as it is. D complement as it is. Now, what is probability of D was given to you? This, look at over here. Probability of D is this one. So probability of D, that is equal to 0.83. You know that probability of D plus probability of D complement, that is equal to always 1. So probability of D complement, that is equal to 1 minus probability of D, and that is equal to 1 minus probability of D is 0.83. That is equal to 0.17. So I don't have any problem over here on the denominator. It is 0.17. Probability of A is given to us over here. Look at here. Look at my pen. So it is 0.82. So let me write it down, 0.82. And minus probability of A intersection D. A intersection D, D intersection A. That is over here. That is this one. So I'm going to get 0.78. So just use your calculator. Whatever the number you are getting, there's a probability of this event. So main important thing is this one, how you can take care of this A intersection D portion from here to here. So please make sure this is nothing but this one. This is nothing but this one. So that's what we mean by this probability. Okay, guys, so this all about the conditional probability where A and B are not mutually exclusive, because B given A means probability of, we are looking for the probability of an event B given that A has already occurred, right? But sometimes what will happen that A and B, they are independent. We are looking for we are working with the conditional probability, but our events A and B, nothing is common for event A and B. So that's what now I'm going to explain to you. So let me again remove this part, clear, stop sharing, and let me go back to my book again. So book is over here. So that's exactly what I explained to you. Look at here, guys. One more example, very simple. You can refer this one by yourself. You can refer to this one. It's not a big deal. And now let me go for the probability of an independent event. In a die tossing experiment discussing on our page 62, we note that, okay, page 62 means just, I explained to you, that is this one, die tossing experiment. That means whenever you have even number, that is twice as likely to occur as an odd number. This is the example. S is equal to 1, 2, 3, 4, 5, 6. Event B is the perfect square 1 and 4. A is equal to number greater than 3, 4, 5, 6. Probability of B given A is equal to 2 over 5 and blah, blah, blah. That's how we can figure it out, right? So this example, again, we are referring to. So it says that in a die tossing experiment discussed on page 62, we note that probability of B given A, that is 2 over 5. Probability of B1 was 1 by 3. Sounds good. And you can see over here, probability of B is different than, these two probabilities are different. Probability B given A and probability of B, 1 by 3 and 2 by 5. They are not same. They are not same, right, guys? Indicating that B depends on A. B depends on A because B has some relation with A. We are looking for the square numbers 1 and 4, but event A says that event A has already occurred, that numbers are strictly greater than 3. So 4, 5, and 6, you don't have any other option. That means B is completely dependent on A. So that was the dependent event. Now we are going to talk about the independent event. So now the independent event, consider an experiment in which two cards are drawn in a succession from an ordinary deck. We have an ordinary deck of 52 cards. Out of these 52 cards, we are going to draw 2 cards on a succession form, right? But with replacement. This word has its own importance. Replacement. That means once I take one card out from the deck of 52, if I take this card, then after I can look at that card and I have to replace that card again. I can keep that card back, right? I can keep that card back. That means my second event, again, I have a deck of 52 cards. It was not like this that I have just one card, but now I have 52 cards, right? Again, for the second event. So in that case, we can say that that's what we mean by with replacement. Whenever it is replacement means it is the independent event. Non-replacement means it is the dependent event. Just keep in mind this thing. Replacement means always independent. Non-replacement means it's the dependent event. Okay, now the first card is an S. How many S's are there? 4 S's, right? Yes, diamond, club, black, and red, heart, right? 4 S's are there. 4 S's are there. Out of these 4 S's, this 4 S's out of the deck of 52, right? So probability of event A is nothing but, what is the probability of event A? Probability of event A, the first card is an S. First card is an S. So 4 S's are there, right? 4 S's are there from the deck of 52. Okay, so I can say 4 divided by 52. Second, probability of B. The second card is a spade. Second card is a spade. How many spades are there? 30 spades are there. from the deck of 52 because the replacement, because whatever card you have chosen over here, now it has nothing to do with this one. Again, you need to replace this one. Suppose you are getting spade over here. You are getting spade over here. Then, okay, fine. You have shown the spade. That's fine. Just keep that card back. It's a replacement, right? Just keep that card back. So again, you have deck of 52. Again, you have deck of 50. Look at over here. 52 is over here. 52 is over here. And second card is a spade. Second card is a spade. We have 13 spades are there. So 13 divided by 12. 13 divided by 12, that is equal to 1/4. So what is probability of B given A? Probability of B given A, that is nothing but just by rule number definition 2.10. B given A is B intersection A divided by probability of A. B intersection A divided by probability of B intersection A. What is probability of B intersection A? First card is an S. Second card is a spade. S and spade. Are you getting me, guys? S and spade. First card is an S. There are 4 S's are there. But the chosen card, S card, chosen card which was S is a spade. It is already given to you that the second card is a spade, right? That means you have just one card which is spade because one spade S is there. So that's why you can say that you have 1 out of, yes, please, probability of B given A, right? So that is equal to the first card is an S, B intersection A, B intersection A divided by probability of A. So it is probability of A, as I told you, that is equal to 1/52. That is the denominator. Then A intersection B, that is nothing but, yes, please, what is A intersection B? The second card is a spade. Second card is a spade. 13 spades are there out of 52. So it is 1/4. And you can see over here, probability of B given A, that is not equal to probability of B. Now that is equal to probability of B. This is 1/4 and 1/4. So please keep in mind this thing that whenever you are replacing the cards at that time, probability of B given A, that is equal to probability of B because A and B are independent events. So always please keep in mind this thing. Same way, suppose this probability of B given A is equal to probability of B. Whatever the number you're going to get, you have over here, whatever the event you have here, first event, this B given A, that means second event. Given A means this is your first event. This is your second event, probability of the second event. A given B, this is your first event. This is your second event, probability of the second event. So always try to understand like this. So whenever two events are mutually, I must say two events are independent, at that time we can say that probability of B given A is probability of B and probability of A given B is equal to probability of A. Always keep in mind this thing when A and B are independent. A and B are independent, assuming the existence of the conditional probability. If that is not true, if they are not independent, means dependent, A and B are dependent, right? And dependent means you can again go back. You can again go back. Based on this one, now I just would like to give you the product rule. I would like to give you the product rule. So product rule is nothing but, look at here. Whatever the rule you have over here, this one, probability of B given A is equal to probability of A intersection B or probability of A. So probability of A intersection B is nothing but probability of B given A times probability of A. That is nothing but your product rule. That is nothing but the product rule. So product rule is mentioned over here. Probability of A intersection B equal to probability of A times probability of B given A. Or probability, I always read other way around. Probability of A intersection B or B intersection A is equal to probability of B given A times probability of A times probability of A, right? Thus the probability of both events A and B occur is equal to the probability that A occurs multiplied by the conditional probability that B occurs given that A occurs. And A intersection B, B intersection A both are equal. So it follows from that theorem that you can write always in this form. Always A intersection B is equal to B intersection A equal to probability of B given that times probability of A given B. A given B. Look at this example. This is the example based on this product rule. Because we have product over here, that's why the product rule is there. Next example. Suppose that we have a fuse box containing 20 fuses, of which 5 are defective. Now look at over here, your box in which 20 fuses are there. Out of these 20 fuses, 5 fuses are defective. If two fuses are selected at random, right? Now 20 in box, 20 fuses are there. In 20 fuses, 5 are defective. You are selecting two fuses at random and remove from the box in succession. You take 2 fuses removed from the box without replacing. Once you are taking these 2 out, means those 2 will not be counted. These 2 could be both are defectives, both are non-defectives, one is defective, one is not defective, something like that. It could be anything. Or first one is defective, second one is non-defective, or vice versa. First one is non-defective, second one is defective. It could be anything. Okay. So that is in succession without replacement. You are not replacing that one. Without replacement means you are working with the dependent event, not the independent event. Please keep in mind this thing, because it is now without replacement. You are not replacing them. What is the probability that both the fuses are defective? You have total 5 defectives. You are looking for the probability for which both the fuses you have chosen, they are defective. Suppose I would say my event A, that the first fuse is defective, and event B, my second fuse is defective. So first fuse defective, second fuse is defective. These are my event A and B, right? So we interpret that intersection B, that means event A occurs, then event B occurs after A occurred, right? A intersection B, we can consider as the event that A occurs and then B occurs after A has occurred. That is my A intersection B. That means this rule. Event A occurs or event B occurs, and then B occurs when given event A occurred. A has occurred. So probability of A intersection B, that is equal to probability of, yes please, probability of A intersection B, that is equal to probability of A times probability of B given A. Probability of B given A. Okay. So first of all, let me find probability of A intersection B. Okay. So probability of the first removing a defective. Suppose your box, in your box, there are 20 fuses. Out of these 20 fuses, 5 are defectives, and you are picking up first one. And what is the probability of getting the first one defective? 5 defectives are there out of 20. So 5 divided by 20, so it is 1/4. So probability of my first event or first fuse which is defective is 5 divided by 20, that is equal to 1/4. That's why the 1/4 is given over here. 1/4 is given over here, right? And now probability of B given A, that means now your second fuse, that one is already gone. So just forget about that. Now you have total 19 fuses in the box. Out of these 19 fuses, one is already defective. That means how many defectives are left out in the box? 4 defectives are there. 4 defectives are there out of 19. That means my second B given A, second event, probability of the second fuse which is defective, given that first one is already defective, 4 defectives are there in the box out of 19, so it is 4 divided by 19. So that's why 4 will get cancelled out, and my answer is 1/19. So that's how you can figure it out, the product rule. Probability of B times probability of A given B, or other way around, probability of A times probability of B given A, like this. Let's go for one more example. That is now intersection of 3 sets. Try to understand this example. One bag contains 4 white balls and 3 black balls. I have, this is my right hand, my one bag, my left hand, second bag. On one bag, I have 4 white and 3 black. 4 white in the first bag. So I would say white in first bag, that is W or W1. Black in first bag, that is B1. Same way. White in second bag is W2. Black in second bag is B2. So let me assign these numbers like this. Now, how many white and blacks are there in the first bag? 4 white and 3 blacks, so total 7 balls are there in the first bag. In the second bag, I have 3 whites and 5 black. So 5 plus 3, that is equal to 8 balls are there in the second bag. So please keep this information with you handy. And now we can proceed further. One ball is drawn from the first bag. This is my first bag. I am picking up one ball blindly. I keep my eyes closed. I pick one ball. I don't know whether it is white or black. And I keep that ball in my second bag. Just like this, I keep my eyes closed. I take one ball from my first bag and keep that ball in my second bag. And now I am getting one ball. Now I mix all these balls. Now there are total 8 balls were there in the second bag. But now by adding this one, now we have 9 balls in the second bag. And if you take this one ball out of this second bag, what is the probability of that selecting ball in your second event that is black? That is a question. So please try to understand this question thoroughly. Now let me read the question again. One bag contains 4 white balls and 3 black balls. As I told you, 7 balls. Second bag contains 3 white balls and 5 black balls. That is equal to 8 balls. One ball is drawn from the first bag and placed unseen. You are not looking at that one. You don't know. You close your eyes. Unseen in the second bag. Put it in the second bag. What is the probability that the ball now drawn from the second bag is black? So what is the probability that you are taking the ball from the second bag? That ball is a black ball. You can change the question. What is the probability of that ball you are chosen now from the second bag is a white ball, right? Let's just stay with the question. Let's find the black ball. That means, first of all, try to understand this thing. As I have assigned B1, B2, that is B1 and W1, black balls and white balls respectively in my first bag. B2 and W2, black ball and white ball in my second bag. Here I have 7 balls, here I have 8 balls. 4 plus 3, 7, 3 plus 5, 8. So these are the scenarios. Now I am picking one ball. I am picking one ball. This ball could be white, it could be black, right? So suppose it is a black ball. In that case, what will happen? That it is B1 intersection B2, because this ball, I am picking one ball from here, and whatever the ball I have put over here, so it could be black. So B1 intersection B2, or suppose this one is Y. If that is not chosen ball, is suppose the first bag is black, and if I keep it over here, I don't know because it is unseen. I have not shown it, right? And if you, so what is the probability? Because if you take the ball from this one, so that black B1 is now here. So B1 intersection B2, it could be any one of these two, B1 intersection B2. Or suppose it is not, I chose the white ball from the first bag, which I don't know. But here it is there in the second bag. So I have W1, because W1 is there over here. So W1 intersection B2, because second ball from the second bag must be black, So this is the event. So you can see over here, probability of, so we are interested in the union of the mutually exclusive events, because if this is done, it has nothing to do. If this is done, it has nothing to do with this one. So A union B form, that is equal to probability of A plus probability of B, because they are mutually exclusive. So this is suppose A, this is B. So that is probability of A plus probability of B, because they are exclusive. So no intersection part. But B1 intersection B2, that is this product rule now. So probability of B1 given that probability of B2 given B1. Probability of W1 given that probability of B2 given W1, right? Now probability of B1, let's count this one, probability of B1. What is probability of B1? B1 means black ball in the first bag. How many balls are there? 4 white and 3 black. 4 plus 3, 7, 3 blacks means 3 by 7. So 3 by 7, look at here, 3 by 7. But here for this one, it's not mutually exclusive. It is mutually exclusive over here, but not here. So it is a conditional probability. Probability of B2 given B1. B2 given B1. So once you take this ball, and that ball is a black ball, and if you take that one if you put that one in the second bag, that means now how many balls are there? 5 plus 3, 8, and 1 ball from the first bag. So 9 balls are there. Out of these 9 balls, how many black balls? Because suppose B2 given B1, given B1 means You are choosing the ball from the second bag that is black, given that first bag ball, B1 was there. First bag ball is a black ball. So now I have one more black ball over here. So 5 plus 3, 8 plus 1. So total 9 balls and 3 white and not 5, but one more black ball from the first bag. So 6 black balls are there. So 6 divided by 9. I hope you understood. It's not that easy. I know it. You need to work on it. You need to practice this one. Probability of W1. Suppose you have to, W1 means first bag. 4 white, 3 black. 4 white means 4C7, 4 divided by 7. Total 7 balls. Now this ball is being kept in the second bag. So how many, and there is white ball. So white ball. So how many white balls are there now in the second bag? 4 white ball and 5 black. So 4 and 5, 9. Out of this 9, but second bag output, whatever second you are taking one ball from the second bag, that has to be black. Look at here, that is black. So 5 divided by 9, and that is the answer. I can explain to you the same thing using the Venn diagram, and that will provide you really, really good answer. Very easy answer, I would say. And that is nothing but, so let me just stop this one. Let me stop sharing and let me share my screen again. Suppose I have my bag one. Bag one. As I told you, I have 4 white and 3 black, right? 4 white and 3 black. And I'm taking, I have another bag. This is my bag 2. Bag 2. What was the situation over here? 3 white and 5 black. Agree? Now suppose the first ball I have chosen, there is a black ball. That's a black ball. You can write if you want B1 and not here, but let me write here B1, black one. B1 and W1, that sounds good. W2, B2 and W2 and B2. Oh, that is black one. So it is total 7. So your probability is 3 divided by 7. 3 divided by 7. Here, suppose that's a white one. It's a white one. So probability is 4 divided by 7. 4 divided by 7. So in bag 2, what will be the situation? 1 black ball is coming over here. So total 6 balls are 6 black balls and 3 white balls. Here now I have previously 3 white ball and 5 black ball. 5 black ball, but now 1 white is coming. So 4 white balls and 5 black balls and 5 black balls. My second ball I'm getting, suppose that is again black. So this is B2, right? Black, there are 6, total 6 plus 3, 9. So 6 divided by 9. And here, suppose it is white. In that case, it is 3 and 3 divided by 9. That's the probability. 3 divided by 9. This you can say that probability of B1, look at over here, B1 intersection B2 intersection B2. That is equal to probability of B1 given probability of B2 given B1. Agree? And probability of B1 is 3 by 7 and probability of B2 given B1, that is equal to 6 by 9. So this is the answer. Means that is this B1 intersection B2. Same way over here. Probability of B1 intersection B2, this is B1 and here it is W2. We don't have to do anything with W2, but if you want to count B1 intersection W2, B1 intersection W2, right? So B1 intersection W2, that is equal to, yes please, probability of B1 and probability of W2 given that B1 occurred. So that is equal to probability of B1 is 3 by 7 and probability of W2 given B1, that is equal to 3 by 9, and that is this number. Same thing will happen over here too. Suppose you have black ball here. So you are getting probability of black ball is, there are 5 black balls, so 5 by 9. That is equal to 5 by 9. And suppose it is white ball, so in that case, your probability will be 4 by 9. 4 by 9. So here what will happen, that probability of W1 intersection B2, that is equal to probability of W1 times probability of B2 given W1, B2 given W1. Probability of W1, that is equal to 4 by 7. B2 given W1 is equal to 5 over 9. And probability of W1 intersection W2. We don't have to do anything with this one, but even though, let me write it down. And probability of W2 given W1, conditional probability, that is equal to probability of W, that is equal to 4 over 7, and probability of W2 given W1, that is equal to 4 over 9, and that is equal to whatever the number you are getting. These are the numbers. That is the answer. As I told you, that our question says that what is the probability of getting B1 intersection B2, or second one is black, right? So W1 intersection B2, intersection B2. So that is equal to probability of B1 intersection B2 plus probability of W1 intersection B2, because they are mutually exclusive. These two events are mutually exclusive, these two events. But here it's a conditional probability. So B1 times probability of B2 given B1 plus probability of W1, probability of B2 given W1. Plug the values. So B1 intersection B2, that is over here. So this number will go here. W1 intersection B2, that is this one. So this number will go here. So whatever the number you are getting, that is the answer. And that must be the same answer, whatever I explained to you without Venn diagrams. So you can understand the concept like this. Now the last part is two events A and B are independent if and only if A intersection B equal to probability of A times probability of B. So two events are independent, two events, if two events are independent, then what will happen? Probability of A intersection B, that is equal to probability of A times probability of B. Probability of A times probability of B. Right, guys? A times probability of B, if they are independent. If they are dependent, only in that case it is B given A. But it is dependent, independent, separate. Right, guys? And now we can apply the same idea of this probability to our next part, that is called theorem 2.12. So let me save this one, and then after I can switch over to the next one. Let me clear this one. So probability of, suppose I have three events, probability of A1 intersection A2 intersection A3. So these three events can be written in the form of, and they are dependent on each other. So they are not mutually exclusive. So probability of A1 times probability of A2 given A1 times probability of A3 given A1 intersection A2, like this. So generalization says that probability of A1 intersection A2 intersection A3 ... up to suppose AK, that is equal to probability of A1, probability of A2 given A1, probability of A3 given A1 intersection A2, probability of A4 given A1 intersection A2 intersection A3 dot dot dot, probability of AK given that A1 intersection A2 intersection A3 intersection dot 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 intersection AK minus 1. AK minus 1. So this is whenever you have the independent, but suppose you have that dependent event. So, but if have independent events, in that case, this probability of A1 intersection A2 intersection AK is equal to probability of A1 times probability of A2 times probability of A3 times dot 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 probability of AK, because they are independent. Probability of AK. And I can give you one simple example. 3 rates, please try to listen to me as per example now. Three cards are drawn in a succession. 3 cards are drawn in a succession. 3 cards. 3 cards without replacement. Without replacement from the ordinary deck of playing cards. Find the probability that the event A intersection A1, A2, and A3 occur. So we are looking for the probability of A1 intersection A2 intersection A3. This probability, where A1 is the event that the first card is a red S. So A1 is the event that the first card is a red S. A2 is the event that the second card is a 10 or a jack. Second card is a 10 or a jack. A3 is the event that the third card is greater than, third card is third card is greater than 3 but less than 7. Greater than 3 but less than 7. So how many elements are there in A3? Greater than 3. That means you have 4, 5, and 6. 4, 5, and 6, 3 numbers are there in A3. How many total different cards are there in a deck? Different colors. One is, yes, spade, then diamond, then red, then black. So 4. So each card, you have 4 types of each card. So multiplied by 4. So that is equal to how many cards you have? 12 cards. So 12 cards are there. 12 cards are there. Here, second card is, first card is a red S. Red and S means it's just 1, right? So I can write like this, that probability of getting, let me write here, that probability of getting A1, that is equal to, it is now without replacement. Am I right? Yes, without replacement means once one event is done, that card is gone. So first card is an ace. So that ace you can find, first card is a red S. Red means red color, heart and diamond, both are red. So there are 2 out of 50. Then my second card is 10 or jack. How many 10s are there in the in the deck? 4 10s are there and 4 jacks are there, right? So 4 plus 4, we have 8, but one card is already gone from the deck, so it is 51. And then after A3, how many cards are there? 4, 5, and 6, less than 3 and greater than 3 and less than 7. 3 cards are there. Each of the different colors are 12. So I would say 12 out of 50. So these are the probabilities. These are the probabilities. Now you can see over here, they are without replacement, means it is a dependent events. That means I can write probability of A1 given that probability of A2 given A1, right? A2 given A1, and probability of A3 probability of A3 given A2 given A1 and A3 given A1 intersection A2. Probability of A1, you know this thing, that is equal to 2 over 52. A2 given A1, because one card is already gone, so actually it is not simply your A2, but it is A2 given A1. That is the meaning, A2 given A1. So that is equal to 8 by 51, because you can see over here, one card is already gone here. So it depends on this one. Probability of A3, it is not actually A3, but actually it is A3 given A1 intersection A2. A1 intersection A2. So that is equal to, here it is 12 divided by 50, and whatever the numbers you are getting, there's a probability of this event. Probability of this event. So that's how you can go for this one. And now I just would like to go over a few of the examples, and then after we can finish this article, and next time we are going to start the last one. There is a base rule. That will be the end of the second chapter. So let me just go over a few of the examples. So let me save this one, and then after we can go for this one. And let me stop sharing. Let me clear the slides, stop sharing, and let me again go to my book. All these things I explained to you, everything is done now. This is very simple, just the electric circuit. Just try to look at this example. It's very simple. I already explained to you. What is the meaning of this one? Look at over here. It says that example 2.73. How can you read this one? This event R is nothing but the convict committed armed robbery, and D is the event that the convict pushed off. So I can read something like this: the probability that a convict who pushed off, always try to read from this side, who pushed off is also committed armed robbery. Is also committed armed robbery. I repeat, a probability that a convict who pushed off also committed armed robbery. A probability of a convict who committed robbery but did not push off. A probability of a convict who did not push off also did not commit robbery. So this way you can read this one. Let's go for one example, example number 2.75. Example number 2.75. Just read this example and we can solve this example. A random sample of 200 adults are classified below by sex and their level of education is attained. Education, male and female, elementary 38, secondary 28, college 32, 45. So we can take the sum of this one, that's male, sum of this one, total number of females in elementary, secondary and college. Elementary total are 38 plus 45, male and female. Secondary here total, like this. In the person, if a person is picked at a random from this group, find the probability that a person is a male. That means here, person is a male. Given that the person has a secondary education. Secondary education, that means here secondary education is 28. So 28 divided by these total numbers, this one and this one, divided by, is a male, secondary, person is a male, given that the person has a secondary education. Person is a male, given secondary education, right? That means I can write this one as, yes, please. Probability of M given S, M stands for male, S stands for secondary. So M given S, that is equal to 28 divided by 28 divided by this number, and secondary means this total number, 50 plus 28, 50, 70, so it is 78, right? So it is 78. So let me write it down like this, guys. Probably it will give you a little more idea. I'm going to repeat the same example over here. Just try to read the example first. The person who is male, so M given S. The person who does not have a college degree, means no college degree, means C complement. C stands for college and C complement. Given that the person is a female, means C complement given that that person is a female, right? So you can say like this. How can you write this one? Male and female. So does not have a college degree. C complement, given that person is a female. So that is F. Right, guys? So I can, let me just stop setting the book and let me again go back and start my whiteboard. So I can write something like this. Example number 2.75. Tabular form says that education male, female, here you have elementary, secondary, college. Elementary, I would like to write E, secondary S, college C, male M, female F. Right, numbers are 3845, 3845, then I have 2850, then I have 2217. 22 and 17. You can see over here, here I have 78 numbers, right? Then after, how many numbers are there here? 88, I think so. 8 plus 8, 16 plus 2, 18, 8 and 1, 88. How many numbers are there here? I think 112, 50 and 45, 95, 95 and then 105 and 712. Yes, here how many numbers are there? So 38 and 40 and 40, so it is 83, right? And how many numbers are there here? 12 and 17. So 17 plus 12, so it is 39. Well, how many total? Total is 200. Total is 200. Here it is 78, 8, 0, 2, 8 plus 2, 10, 17, 17 and 3, 20. So 200. Right, guys? Now my first question says that, or I can write it down over here, not here. A is equal to person with probability of male who has a secondary education. Male and secondary education. Right, guys? Male given that secondary education, that is equal to probability of M intersection S divided by probability of S. M intersection S, that is M and S, male and secondary, so 28. That is equal to 28 divided by 200. 200 divided by secondary education, that is equal to 78. So 78 divided by 200. This will get cancelled out, so you're going to get 28 divided by 78. Then after, same way I can go for the another one, that is person is a male. Where is it? Okay, the person does not have a college degree. So does not have a college degree. Given that the person is a female. Person is a female given that he is not a male. Or you can write female or not a male, same thing. So that is equal to, yes please, person does not have a college degree. So here, what is the total over here? Is 39, but this total is 95. Am I right? No. What is the total here? Please help me. Yes, please. Does not have a college degree and he is not a male. Does not have a college degree and he is not a male. Right, guys? That means I can write that is equal to does not have a college degree. He is a male. So that is fine. He is not a male. That means he is female. Does not have a college degree. So no college degree, no college degree. No college degree, no college degree. So what is the total? Here it is. Help me. Here it is 78 plus 83. Right? Does not have a college degree. College degree total. This one. Let me just try to work on this one. College degree, does not have a college degree. And he is not a male. So he is a female, does not have a college degree. So let me remove this college degree from the total number. So college degree I have to remove from total number of, and she is a female. Female means, or not male, male is 88. Male is 88. So not male means 112. So 112 divided by 200, you can say, divided by 200. And does not have a college degree. Numerator. How can we fix the numerator? Does not have a college degree means either they have these two, because they are female. They are female, that is already given to us. So we have to just concentrate over here. This total is 95. So 95 divided by 200. This will get cancelled out. So you're going to get 95 divided by 112. So because just female, right? No male means female. So total, there are 95 females, those who are having elementary or secondary degree, but does not have a college degree. So 95 out of 200 and this one. So that's why you can solve this one. That's fine. Then after example 2.76 is quite simple homework, 2.76 homework. Then after, let me go for one more example or a couple more examples and we'll stop. So let me go through example number 2.77 also homework. 2.77 homework. And let's go for example number 2.80. So example 2.80 says that, what is 2.80 guys? So let me just read this example for you. I can stop sharing this one and let's go with the book. So book says that, yeah, this example is homework. This one is homework, and 2 point, as I told you, which one, 2.80. Okay, 2.80. The probability that the automobile being filled with gasoline also needs an oil change is 0.25. See, probability that an automobile being filled with gasoline also needs the oil change. So gasoline with oil change is 25, which means intersection. The probability that it needs a new oil filter is 0.40. Third one, right? 0.40. And the probability that both oil and filter needs, that is 0.14. So please keep in mind this thing. That means I can say something like this. Okay, I will write later on. If the oil has to be changed, oil has to be changed. Look at over here, guys. If I say that C is the oil change and F is the oil filter change, C stands for change of oil or oil change, and F is the filter change or oil filter change, oil filter needed. If the oil has to be changed, that means that is the first probability. What is the probability that the oil filters? So we are looking for probability of F given C. That's the meaning. If the new oil filter needed, other way around. So F is needed. What is the probability that oil has to be changed? Oil has to be changed. That means now it is C given F, right? So this is the example in which we have the reverse order. So let me go for this example. Let me again stop this one and let's go to our screen. So now example number 2.80. Consider the event that an oil change is needed. Oil change is needed. Consider the event that an oil filter is needed. Oil change for C and filter F is needed. So probability of F given C is equal to probability of F intersection C divided by probability of C. And B is probability of C given F, that is equal to probability of C intersection F divided by probability of F. Here it is, probability of F intersection C that is given in the book, that is equal to 0.4. And probability of C that is equal to 0.25, and you are getting the answer. C intersection F is 0.14 and probability of F is equal to 0.40. And that is the answer. So that's how you can solve this example 2.80. 2.80. All other examples, they are just of similar kind. So I don't think that you need my help for rest of the examples. But even though if you want, I can go over one more problem, and I think that will be the end. So probability example 2.83 homework, 2.83, examples 2.83, 81, sorry, 81 and 2.83 homework. And now let me go for one more example, that is 2.85. 2.85. 2.85 says that the probability that a doctor correctly diagnoses a particular illness is 0.7. Given that the doctor makes an incorrect diagnosis, the probability that the patient files a lawsuit is 0.9. What is the probability that the doctor makes an incorrect diagnosis and the patient sues? I repeat, example 2.85. The probability that a doctor correctly diagnoses a particular illness is 0.7. Doctor is good in that case. Given that the doctor makes an incorrect diagnosis, the probability that the patient files a lawsuit is 0.9. What is the probability that the doctor makes an incorrect diagnosis and the patient sues? Okay, guys, so let me write this one. Example number 2. Let me change this color now. So example number 2.85. Consider the events like this. Suppose A is the event, the doctor makes a correct diagnosis. The doctor makes a correct diagnosis. Event B is the patient sues. The patient sues. And we are asked, the doctor makes an incorrect diagnosis, means A complement, intersection, patient sue. That is equal to probability of A dash given that probability of B given A dash. Probability of B given A dash. Probability of A dash, doctor, 2.85, where is it? Yes, doctor makes probability that the doctor correctly diagnoses a particular event is 0.7. Right? Doctor makes the diagnosis that is equal to 0.7. So that means probability of A is equal to 0.7. So probability of A complement is equal to 1 minus probability of A, that is equal to 1 minus 0.7, that is equal to 0.3. So let me use over here 0.3. And probability of B given A complement. B given A complement, that means doctor makes a incorrect diagnosis and patient sues. So that probability is given to you, that is 0.9. So that is equal to 0.9. So it's a product rule example. Product rule example, theorem 2.11. 2.10 or 11, you can say. So whatever the number, that is 2.7, so 0.27, that is the answer. So it is simple. So this way, guys, you can solve the rest of the examples, whatever I give to you, 2.88 in homework, 2.88 also in homework. And I think this homework is enough. And next time, so let me stop over here, guys. And next time we're going to start the new article, that is the Bayes rule. And that is the last article of this chapter. And then after, first internal exam maybe, and then after we will start the new chapter, that is chapter number 3. The lengthiest, very lengthy chapter, one of the lengthiest chapters. we are going to finish next time. Thank you so much, guys. Let me save this one, and this is the folder. I have saved it, and let me clear everything now. Let me stop sharing. And thank you so much, guys, and I'll see you next time. So let me stop my recording too now.